All right, so in the last video we talked about taking a space curve given by some vector function r of t and reparametrizing it with respect to arc length. We want to do an example illustrating that. So we're given this arc curve here, r of t equals this guy. Notice it's a plane curve, there's only two components here. And we want to reparametrize this with respect to arc length, measured from the point 1, 0 in the direction of increasing t. So we'll kind of talk about what that means when we get to that point. Notice right now the vector function is given as a function of t. We would like to turn that into a function of s. That's our goal. So how do we do that? Well, we need to begin by finding our arc length function to get s of t. S, the variable s, which we think of as s of t, is equal to... Now, we want to measure arc length from this point, the point 1, 0. And by inspection, again, we're looking for a value of t that we could plug into this that would give us the point 1, 0. By inspection, we could see that that would be 0 itself. And, plug it in, see if that actually works. We would get 1, 0 here. And the upper limit of integration we know should be t. Now the next thing that we need is the magnitude of r prime. So let me do that off to the side. What is the magnitude of r prime of t? Well, the first thing that we need for that is r prime of t. So what is that? I'm doing this in kind of a weird order here, because when you read this, it's going to go from the bottom up. But what is r prime of t? Well, r prime of t, you can approach these derivatives in a couple of different ways. You could use the quotient rule on both of them, for example. You can bypass the quotient rule in this case and do the chain rule instead. But what we should end up with is negative 4t over t squared plus 1 quantity squared there. And then we should have 2 minus 2t squared over, again, t squared plus 1 quantity squared. So I'm going to bypass, all the nitty-gritty steps that we would have done in Calculus 1 evaluating these derivatives, but I encourage you to double check, make sure that that looks correct. Okay, going back up here, what we need is the norm or the magnitude of this vector. So it's the square root of the sum of the squares of these guys, negative 4t over t squared plus t squared plus 1 squared plus 2 minus 2t squared over t squared plus 1 quantity squared, everything squared, and big square root there. Okay, now there's a significant chunk of algebra that happens here, and I'm going to kind of jump through several of those steps for the sake of time, but you should have the algebraic skills to handle this. So if you were to square both of these, first of all, notice you're going to get the same denominator, t squared plus 1 quantity to the 4th. And then if you square the numerators, added everything together, you would end up with a polynomial that can be factored. And after factoring it, you're going to get this, 4 times t squared plus 1 quantity squared over t squared plus 1 to the 4th power, just like that. Okay? Again, there's a significant chunk of algebra happening right here, and I'm just leaving that out. You should be able to fill in those gaps. Notice that after factoring, we have some nice cancellation that happens here, so we're going to lose this factor of t squared plus 1 squared up here. T squared plus 1 squared is what will be left down here, and the square root will cancel that. Square root of 4 is 2, so this becomes 2 over t squared plus 1 in the end. And again, when you take the square root of something squared, normally you have absolute values around that. Notice I left the absolute value off here. Can you justify that? Why is it okay for me to do that here? I'll let you figure that out. All right, so that is going to become our integrand up here. 2 over t squared plus 1. I'm sorry, I have to change my variable. Let's make that a u and then du, since we're already using a t right here. Okay, this should be a familiar integral. This is going to give us an arc tangent. So if I do my integration, I should end up with 2 arctan or tan inverse of u from 0 to t. And I know that the arctangent of 0 is 0, so this is not going to contribute anything. This becomes 2 inverse tangent of t. Okay, now all that's left is to take this, s is equal to 2 arctangent of t, and I want to solve this for t. It only takes 2 steps to do that. Divide by 2, and then take a tangent of both sides. T is equal to the tangent of s over 2. Okay, now what's left to do here is to take this expression and substitute that in for the t's that show up in my r of t, my vector function. So r of s, reparametrizing now. And again, here's r of t up here. It's going to look like 2 over t squared plus 1. So that's going to be tangent squared of s over 2 plus 1. And then minus 1. I have a minus 1 there as well. Over here, 2 times t. So that would be 2 tangent of s over 2 over t squared plus 1 again. So that's tangent squared of s over 2 plus 1. I could technically leave it that way if I wanted to, or if I were to do some trig identities on this thing. I know that tangent squared of something plus 1 is equal to secant squared. So I could write this as 2 secant squared of s over 2, not plus 1, just 2 over secant squared of s plus s over 2. And then I could write this as just 2 tangent of s over 2 over secant squared of s over 2. Okay. Now, it's fine to leave it in this form. I could just, leave it in as is. I could have even left it like this if I wanted to, and we're essentially good. However, and I'm going to let you fill in some of these blanks here. This has we can simplify this in a slightly different way. So, in fact, maybe we'll go ahead and work through some of these steps. Actually, no, I'm going to let you fill in some gaps here. So I'm going to say ... With the appropriate trig identities, we can actually show that this thing simplifies to something much, much nicer looking. It simplifies to cosine of s sine of s. Okay? I realized I was off the screen. Not at all obvious why, but if you're savvy on your trig identities, you can actually get to here from here. And I went this route simplifying before, but if I were to go, I forgot my minus 1 over here. It should be a minus 1. If I were to approach this in a slightly different manner, for example, this guy right here looks kind of similar to maybe a double angle formula for tangent. There's other identities that could be used to simplify this. See if you have the strength in trigonometry to get from here to here. But if you can, the benefit of knowing this is that this thing right here is a parametrization for the unit circle. And again, the curve given by this function, r of s, is the exact same curve that we would have gotten from r of t. It's just that we're parametrizing them in different ways. So the kind of interesting thing about this is once we got down here, now we can picture what this curve actually is. It's not obvious from this parametrization that this would be a unit circle. Okay, if anybody struggles with kind of doing this derivation, getting from here to here, maybe ask a question about it in the discussion topic for the chapter 13 lecture videos, and I can explain it in more depth there. Okay, all right. So moving on to the next part of this section. So again, in this section, we titled it arc length and curvature, and we haven't talked about this concept of curvature. Curvature is a really useful concept when it comes to space curves, and the term also applies to plane curves as well. But basically the idea of curvature is it's a quantity that represents how tightly the curve is turning at a given point. Specifically, we want it to be a non-negative value, and the larger the number that represents curvature, the tighter the curve is at that particular point. This concept only applies to something that we call smooth curves. So I'm going to give you the definition of smooth right here. If you have a parameterization for a curve r of t, we say that it's smooth if smooth on an interval I if the derivative of our vector function is both continuous and non-zero on I. Now, the continuous part might seem a little bit obvious why we would want that. The non-zero part may not seem as obvious. The reason for that is because we want to think of curves, and we're going to explore this more in 13.4 in the next section. We're going to think of these curves as paths, and a point is essentially going to be moving along that path. And what we're going to show at the very beginning of 13.4 is that if r of t represents the position function of a point on this curve at a given time t, so at that point we think of the parameter t as time, then the derivative, r prime of t, is going to represent the velocity function of that point at a given time t again. And if that velocity function is ever equal to 0, that means that the point has stopped. There's no motion happening. But we want to imagine these as always having some kind of motion. Curvature has some close ties to velocity, as we're going to see in the next section. So that's kind of why we want the non-zero part. Now, let's think about how we would define this. So looking at this example, this image right here, and imagine this point kind of moving along this curve. Notice that this part of the space curve right here is not a super tight part of that turn. It's kind of gradually turning this direction. And if you follow the unit tangent vector at each of these points, you're going to see that the tangent vector will turn with that curve in order to stay tangent to it. But the rate at which it's turning is not what I would necessarily say fast. I would say that it's turning relatively slow. That's a non-formal term that I'm using there, slow. Notice, however, as the space curve kind of takes a tight turn right here, the direction of that unit tangent vector changes pretty rapidly. It goes from pointing this direction to something that's looks like it could be even more than a 90-degree turn, just going from here to here. So that tight turn corresponded to a rapid change in the direction of our unit tangent vector, whereas these gradual turns correspond to a slower change in the unit tangent vector's direction. Well, now think about when I say the word change, or more specifically rate of change, slow change versus quick change, that should make you think of a derivative, because remember, that's what a derivative technically is, a rate of change. And so we would like to make some sort of connection between the rate of change of our unit tangent vector and the curvature. And there's one important thing to consider here, though. Rates of change involve two quantities, one quantity changing with respect to another quantity. So what should that second quantity be? The first one is our change in our unit tangent vector, but we want that to change with respect to arc length, because that's basically saying if we've covered this amount of distance and only observed this amount of change in our unit tangent vector, we want that to come out to a small rate. But if we've made a short, or we've covered a short distance and seen a drastic change in our unit tangent vector, we want that to correspond to a large rate. So essentially, we're looking at the change in our unit tangent vector with respect to arc length as this point traverses this curve. That's going to be how we define the curvature of this curve at a given point. But that's not quite enough. We did say earlier that we would like the curvature to be represented by a positive number. And so we end up taking the absolute value of that derivative. Now, so here's our definition. Curvature is equal to the absolute value, curvature at any given point, it's equal to the absolute value of the derivative of our unit tangent vector function, remember that's a function of t, with respect to s, arc length. Okay. Now, one other thing worth asking, why would we care that this be the unit tangent vector? Why not just any tangent vector? You know, why don't we just look at the change in r prime with respect to arc length s? And the reason for that is because r prime can be changing in two different ways as this point moves along this curve. Remember, there's two different ways of measuring there's two different quantities that we associate with a vector. There's direction, and then there's also magnitude, right? So r prime can be it can be experiencing a change in direction and magnitude as this point moves along. But magnitude shouldn't have any impact on the curvature of this curve. We're going to see in section 3.4 the magnitude corresponds to essentially how fast this point is moving, but not how quickly it's turning. The benefit of the unit tangent vector is that it normalizes all of those tangent vectors so they all have the exact same magnitude. The magnitude of all of these vectors is 1. That means when we look at the derivative of t with respect to s, if the magnitude of these vectors is not changing, then this derivative is only taking into account the change in direction of that unit tangent vector, and that's what we care about. Okay? So this is our definition, again, of curvature. It turns out it's not the most useful way to think of curvature, however, and we're going to derive a few different formulas for calculating this thing. Okay? So one way we're going to do this is to remember that this curve here, r of t, as we would normally think of it, can be reparametrized with respect to arc length. So that's where we're thinking of r as a function of s. That's kind of where this derivative would ultimately come from. But you can think of r as a function of either s or of t. And as we saw previously, your arc length function, s of t, puts arc length in terms of t. So if we think of this, the function that this would have come from, we would have had to reparametrize our unit tangent vector function with respect to s. Right? But s by itself is a function of t. And so we can think of capital T, our unit tangent vector, as a composite function, t of s of t. Okay? Now, again, remember, this is a vector function. So if I were to differentiate with respect to that independent variable t, then I would use the chain rule here because this is a composite function. So what does dt look like? Well, it's the derivative of t, but I keep s the same, and then I multiply by the derivative of this inside function, which would be ds dt. It looks like this. dt dt is equal to dt ds, ds dt. Solving this for dt ds, because this term, this factor right here, is what's showing up in our curvature formula. I would divide both sides by ds dt, and then curvature would be the absolute value of that. So curvature is defined as dt ds in absolute value, or the magnitude, really. It's a magnitude of this vector. But this vector inside here, dt ds, is the same thing as dt dt over ds dt, and each of these is represented a different way. dt dt is the same thing as t prime of t. And ds dt, we showed from our arc length formula, is the same thing as the magnitude of r prime of t. Remember, we kind of derived that earlier in this section. Okay, so that leads to a more useful way of evaluating curvature, which is to use this formula. And we're actually going to come up with even more useful definitions, or not definitions, but formulas for curvature than this one. But we are going to use this one for one little application that's going to be useful in a little bit. Okay, so remember this little formula right here. Come on, page. There we go. All right. So this example here is one that appears in your book, and we're going to go through it because it's an important relationship between curvature and circles. Okay, so it says show that the curvature of a circle of radius a is 1 over a. And one thing to point out here is when we evaluate curvature, curvature is a function of t. Or a function of s, depending on which formula you use. In other words, curvature can change depending on which point on a curve you're talking about. But if you think about a circle, it doesn't really make sense for the curvature of a circle at any given point to be different. You know, a circle naturally should have the same curvature here as it does here, because the curve here is not any sharper or less sharp than it is here. So it kind of makes sense that the curvature function for a circle should be a constant function. But again, how do we do this? Well, it's important to remember how to parametrize a circle, because everything done here is in terms of vector functions. The parametrization for a circle of radius a is a cosine of t, a sine of t, or that's kind of the standard parametrization. Okay. Now, what do we need in order to evaluate curvature? Well, we need t prime and we need r prime. So let's find r prime first. What is r prime of t? R prime of t here would be negative a cosine of t. Negative a sine of t, and then a cosine of t. Okay. Next step, we're going to need to find the unit tangent vector so that we can differentiate it and get t prime. But in order to do that, I actually need r prime and its magnitude. What is the magnitude of r prime of t? Well, that would be equal to the square root of a squared sine squared of t plus a squared cosine squared of t, factoring that a squared out, and then taking the using the Pythagorean identity, sine squared plus cosine squared. This whole thing simplifies down to a. Technically, it should be the absolute value of a, but remember, we're talking about a circle of radius a. The context here implies that a is already positive, so there's nothing really to do there. Okay, now let's find our unit tangent vector function. So t of t is equal to r prime of t over the magnitude of r prime of t. Okay, well, here's r prime, negative a sine of t, a cosine of t, and I want to divide that by my magnitude, that's scalar a. Dividing that by a is just going to remove the a's here and here. So this becomes negative sine of t cosine of t. Okay? Next up, we need the derivative of this. So t prime of t, the derivative of this guy would be negative cosine of t, negative sine of t. Okay, we're almost there. Now we just need curvature. Curvature is equal to the magnitude of t prime of t over the magnitude of r prime of t. We found the magnitude of r prime. We didn't find the magnitude of t prime. Let's maybe do that right here, just so everything is on the left side before I start plugging stuff in. What would that be? Well, it would be negative cosine of t squared, which is just cosine squared of t, plus negative sine of t squared, which is sine squared of t. This whole thing is just equal to 1. Okay, so putting that all together, we get 1 over, and again, r prime had a magnitude of a, 1 over a. And that's what we were trying to show. Now, if you think about this, that actually makes a whole lot of sense, because this basically says that the larger the radius, the smaller its curvature. There's an inverse relationship between those two things. And to me, that makes a whole lot of sense, because if you think of this circle up here as a large circle, and then compare that to a much smaller circle, and then if you think of the distance traversed from here to here, s, that would correspond to, this point moving around this circle probably a couple of times, to have the same arc length. Well, that unit tangent vector is changing much more quickly in this small circle, even though the linear distance covered is the same as this larger circle, where a far less drastic change in t would be occurring. Okay, That's going to be all the time we have for this video. In the next video, we'll move on to some more commonly used formulas for curvature, and then we also need to talk about unit normals, binormals, and a few other things to finish out this section. But that's going to be it.